Welcome back, guys. This is going to be the third and final installment on this lecture series on solving systems of equations using matrices. In the first video, we introduced graphing two linear equations to see where those two lines intersected. In the second video, we introduced the idea of a matrix, how to describe them using the dimensions, the number of rows by the number of columns, and also converting a system of equations into a matrix. Okay, so in this section, we're actually going to be starting to perform some mathematical operations on those matrices in a process that's called the Gauss-Jordan elimination process. Okay, now just to give you an overview on this process, to solve a system of equations using matrices, we're going to want to take the system and convert it into a matrix. Then we're going to start using some manipulations that we call row operations until we have obtained something that looks like what I call Swiss cheese. Okay. That's not going to make a whole lot of sense right now. And to tell you guys the truth, I would say that this process is not the most complicated thing, but there are a lot of little steps that you have to watch out for. So as we proceed through this, just remember, we're going to get through one example, and I'm just going to show you the steps of how to manipulate the matrix. And then if you remember that process, well, then taking on other examples after that should be following that same pattern, but the numbers will be different, and so that's where the changes are going to occur. Okay, so if you memorize the process, then everything should be fine. Okay, so let's begin. If we look at the bottom left, we can see that we have a matrix here, and it's a 2x3 augmented matrix. Okay, remember that each of the rows in the matrix indicate an equation for our system. What I mean by that is, let's go ahead and just highlight this first row here. Remember that this came from an equation which we could, if we wanted to, rewrite as 2x plus 5y equals 12. Similarly, we could say that the second equation, or the second row of this matrix, came from the equation negative 3x plus 6y equals 9. Okay, so that should be pretty familiar at this point if you've gotten some practice in the homework. Okay, but with these row operations that we're going to start performing, we're going to change the numbers in this matrix until we get something that looks more like this, where we have the first row with a 1, a 0, and then a number here. And then the second row will be a 0, 1, and then another number. Okay, now we don't really know what those last two numbers in the third column are going to be for any given problem. But what we're trying to focus on is, can we do some operations, perform some mathematical tricks to get this 1, 0, 0, 1 pattern, as you see here in this rectangle. And so if I were to just show this rectangle to you, and you weren't familiar with any of the math that we're going to talk about here in a second, you might say to yourself, this little rectangle looks like Swiss cheese. And that's why I say we're trying to get Swiss cheese out of these matrices. Okay, what mathematicians call this matrix is the reduced row echelon form of our original matrix. But for our purposes, you can go ahead and just think of it as we're trying to get Swiss cheese, and that's going to tell me the solution for my equation. How is this going to tell me the solution to my equation? Well, remember that the first row is an equation. And so if I translate this matrix back to an equation, I have 1x and I have 0 y's, and that's equal to 1. If I look at the second row, I have 0 x's and I have 1 y, and that's equal to 2. So if you remember that in all of this process that we're going to get into, that what we're really trying to do is find the ordered pair which indicates the intersection of two line segments, then these two lines will intersect at 1, 2, that XY pair that we can just read out of the reduced row echelon form matrix. Okay, so some fancy terminology here, but how do we get there? That's going to be the hard part. Okay, so let's look at the big picture. There are a few set of row operations that we can perform to get RREF, reduced row echelon form, or Swiss cheese of the system. So we're looking for a pattern that eventually looks like this, but we have some simple row operations that we'll be able to perform. Rather than taking you through this PowerPoint, I'm going to switch us over to pencil and paper so that you can see this process worked out by hand from start to finish. And like I said, we're going to do this first example. It may go a little quick, so you might have to pause the video at certain points just to make sure that you're understanding. But then once we get into the second example, I think that then it will start to sort of crystallize what we're actually doing and how we're going to change the matrix to get reduced row echelon form. Okay, so let's begin. All right. Right now, we're going to be asked to solve the system of equations, and we may be given a system of equations like what is provided here. It's a little bit blurry. Let me go ahead and make that a little bit more solid for you guys. What has happened? Okay, there we are. So we're starting with this system of equations. Remember, you're going to have two linear equations, and they both have to be in standard form. So we have ax plus by equals c, and we have ax plus by equals c. Okay, so the first thing that we're going to want to do is just always make sure that that's in standard form. Ax plus by equals c. Okay. Then we want to go ahead and convert the equations to a matrix. So remember that each of these equations will become a row in the matrix. So I'm going to put 2, 5, and 12 here. I will put -3, 6, and 9 down for the next row. Okay. So now we have our matrix. Now is the hard part, which is remembering what do we need to do here. So I'm going to make a little note here that our goal is to obtain reduced row echelon form, which is 1, 0, and then a number, a 0, a 1, and then a number. Okay. And currently, our matrix doesn't look anything like that. All right. So what we want to do first is maybe we can focus on these first columns here. Notice that for our goal, we want to get a 1 here and a 0 here, and I will tell you it is easier to find the zeros first, okay? So we're going to take 2 steps to do that. First, if we look at our matrix right here in the first column, this is the X column, okay? Eventually we'll get a 0 right here, but the way we do that and the reason why that this is called Gauss-Jordan elimination is because we need to eliminate something, cancel it out to get a 0, okay? But right now, 2 and -3, if we were like to combine them, they wouldn't cancel out to 0. So what we need is to sort of match these two numbers somehow so that they're the same number but with opposite sign. So think about this for a moment. If I had, for instance, a 10 plus a -10, so that would be really nice because they would cancel out to 0, and I'm trying to get that 0, okay? Right now, I don't have these numbers matching, but these are just equations. And the rules for equations say, well, you can multiply your equation by any number, and it won't change the final answer as long as you multiply that number across the entire equation. So every single term needs to be multiplied by that number. So we're going to sort of leverage that fact and just do a quick trick, which is take this number 3 that's in the bottom row, and we're going to place it right here at the top row. Then we're going to take this number 2, or whatever this number happens to be. It happens to be a 2 in this problem. We're going to place it here in front of the second row, okay? And what we're going to do is multiply or distribute these numbers through every other value in that row. So I'm going to multiply 3 times 2, 3 times 5, 3 times 12, and those are going to give me new values that I'm going to write in a new matrix. I'm also going to take 2 times -3, 2 times 6, and 2 times 9, okay? And the reason for that is going to be hopefully obvious very shortly, but let's go ahead and just do that. We're just doing this crisscross pattern where we take the 2 here and we take the 3 here, okay? But we're not really concerned about the signs just yet, okay? So if I do this, let's go ahead and just multiply this 3 through the entire top row, okay? 3 times 2, we just put it in our calculator, 3 times 2 is 6. So I'm going to write a 6 here, okay? 3 times 5 is 15. So I'm going to put a 15 down. And then 3 times 12, 3 times 12 is 36, okay? Once you have that down, we're going to take this 2 and multiply it by each of these numbers in the bottom row. So we're going to take 2 times 3, or 2 times -3 rather, 2 times 6, 2 times 9. So 2 times -3, and we're going to put a -6 down. 2 times 6, we're going to put a 12 down. 2 times 9, we're going to put an 18 down. Okay, and that is going to be our new matrix. Okay, well, why did we do that? Well, the Gauss-Jordan elimination says that we need to eliminate something. And the only way we're going to be able to eliminate something is if we take these numbers here and add them down the column. So now, really, let me go ahead and write the third step, which we just did, is that you need to multiply a set of numbers so that the x coefficients right here in this first column, so that they match each other, but have opposite signs, okay? And the way we did that was just by crisscrossing these numbers here. You could think of it kind of like a cross multiplication process, but usually I kind of avoid that phrasing because I think cross multiplying means a lot of things to a lot of different people. But we're just crisscrossing those numbers so that we know that 3 times 2 and 2 times 3 will be the same number here. But what we really want is those to have opposite signs, because the next step, the fourth step, is to add the numbers down the column. So I'm going to think about these numbers here that are in this new matrix. I'm going to add them. So add down. Okay. So you can grab your calculator for this. And we'll do 6 plus -6. That gives me the 0 that I was looking for. Okay. And then we'll just go ahead and add the 15 plus the 12. We'll put a 27 down. We'll put 36 plus 18. We'll put a 54 down. Okay. Now, right now, all of these numbers are kind of changing all over the place, but don't worry, we need to focus on one thing at a time. What we're trying to do is get this 0 here in this bottom row. And guess what? We have a 0 right here in this row of numbers. So once we add the numbers down the columns and we get the elimination, then we're going to replace row 2. We're going to build from the bottom up. Okay, so we're going to replace row 2 now, and we'll get a new matrix. So what I mean by that is, let's go ahead and draw a matrix. And 0, 27, and 54 are going to go right here. 0, 27, and 54. Okay. You may ask me, well, what do I put in the top row then? Okay. And to make this easier, I would say just take the numbers from the top row of the previous matrix we had. Okay. So we could take 6, 15, and 36 and leave those alone. Okay. We added the numbers down the columns. We replaced row 2, but row 1 is going to stay the same. Okay. So we're kind of one step closer to getting reduced row echelon form because we got this 0 here. We'll worry about this other 0 next, and we'll worry about the ones last. But we're just trying to come up with this pattern of eliminating these numbers here and here. Okay, so now we're going to kind of start the process over again. So I'm going to clear my calculator, and this time I'm going to focus on the second column, which is my y coefficients, right? And right now, these are not the same number, so I won't be able to eliminate anything until I do some sort of modification. So once we're done with step 4, we need to go sort of back to step 3. So let's say step 5, realistically, is to multiply a set of numbers so that these y coefficients match each other with opposite sign. Okay, well, how do I choose which numbers to multiply? Well, we can just employ that cross multiplication method, that crisscross pattern, to get that matching set of numbers when we multiply. So if I take this 27 from here, and I multiply it on the top row, and I take this 15 here, and I put it down here, then eventually I'll do 27 times 15 and 15 times 27. You might not know what that is, but 27 times 15 and 15 times 27, it's going to be the same number, okay? So if you're okay with that, then the next thing you do have to watch out for is 27 and 15 are going to be a positive number when you multiply them. 15 and 27 also going to be also going to be positive. We want one of them to be negative. We don't want them to have the same sign. We want them to have opposite sign. So if you need to change it to make an opposite sign, you need to throw a negative sign into this multiplication problem, okay? And that's going to fix it. So right now, that might seem a little bit strange, but if you just trust me, we'll see how this will work out in the next step. So the next step is just to go ahead and run through that multiplication. And remember, we're just distributing or multiplying across the row now, okay? And one thing I might have to note here is that these numbers are going to get really big. Do not worry about the size of the number. We're going to make them small at the end. But for now, let's just do the process and trust the process and see how things go, okay? So here I'm going to take negative 27 times 6. I'm going to put negative 162 here. I'm going to do negative 27 times 15. Negative 27 times 15. I get negative 405. Big number, but not unreasonable. Okay. Negative 27 times 36 is going to be negative 972. Okay. So if you need to make a little bit more space for yourself, you totally can. But then we'll move on to row 2. We're going to take 15 times 0. 15 times 0 is 0. 15 times 27 is going to be 405. Guess what? These guys match, but with opposite sign, and that's what we were looking to do. That's why we do this crisscross pattern and then check to see if we need to throw a negative in there. And then we'll do 15 times 54, and that's 810. Okay. So pause if you need to, just to catch up emotionally or catch up to what I've written down. Make sure that you are writing this down exactly the way I wrote it, because if you make one tiny little mistake, this is going to be a very frustrating process. Okay. But once we multiply that set of numbers together and we get the y coefficients to match, but now they have opposite sign, we're basically doing a redo of steps 3 and 4. So now we're going to do step 6, which is just to add the numbers down the columns again. Then we're going to use the new numbers that we have to replace row 1. And we'll see in a minute why we're going to do that. So if I just draw a little line here and I say to myself, okay, well, negative 162 plus 0, remember we're adding, we get negative 162. 162, okay? Then if we take negative 405 plus 405, we get 0. Negative 972 and plus 810, we get negative 162. Okay, so we have a row now of 3 numbers. And if we look over here at our goal, let's just look at this top row. We have 1, 0, and then some number. We have something 0, and then some number. We're looking to get that 0 in the middle. So this is going to replace row 1. Okay. So by taking this block of numbers and this block of numbers, okay, these 2 rows that you got, we're going to use those and put them together to make our second to last matrix. Okay, so this 0, 27, and the 54, and then the negative 162, the 0, and the negative 162. Or you could say, well, I think what we did before was this would replace row 1, but row 2 is going to stay the same. So like just to be consistent, and I think that's what I do in the PowerPoint, I'm going to say to myself, let's just stick with, this will be the new row 1. So I'm going to put negative 162, 0, negative 162. And then I will keep row 2 the same. So I'll leave this as 0, 405, and 810. I'm not going to make a huge difference here. Okay. So this is the penultimate, which is a fancy way of saying second to last step. Okay. So let's take this matrix. Let's go over to a new sheet of paper if you're okay with these steps. And the important thing is that we have a 0 here and a 0 here, because getting the 1s is going to be very easy to do at this point. Okay. So I'm going to rewrite this matrix that we have. We have negative 162, 0, and negative 162. We also have 0, 405, and 810. Okay. Now I've been dragging you guys through this process, and you've just trusted me, and hopefully it kind of makes sense that we can multiply any number that we want across the row, because the row is just an equation, and we can always multiply any number we want into an equation as long as we multiply every single term by that number. Okay. Well, multiplication is very similar to division. In fact, they're sibling operations. So if I can multiply a number into an equation, then I can also divide a number out of that equation, right? And we've done this before. So I'm just going to write here that our goal is to get reduced row echelon form, which looks something like this. Okay. So let's focus on one row at a time. Let's focus on this first row. Now, I want to change this number into a 1, okay? Either through multiplication or division. Well, the easiest way to take a number, divide it by something, and get a 1 is just to divide that number by itself. So I'm going to divide this entire row by negative 162. or whatever this number happens to be, okay? Because anything divided by itself will give you 1, okay? So let's see what happens when we do that division, okay? So I'm going to write a new matrix here, and I'm going to divide each of these 3 numbers by negative 162. So negative 162 divided by negative 162, something divided by itself, gives you 1. Then we're going to do 0 divided by negative 162. That's going to be 0. Finally, negative 162 divided by negative 162, well, guess what? We just did that, and it's a 1. Okay. So now this final matrix is looking like reduced row echelon form. Okay. So we have to ask ourselves, well, that was all well and good. In this second row, how can I turn this number, into a 1 through division? Okay, well, the answer should be a little bit obvious, or it should make kind of sort of sense. And that is, if I divide this number by itself, it will turn into a 1. Okay, so I'm going to take all of these numbers and divide them by 405. So 0 divided by 405, you could put in the calculator, 0 divided by 405 is 0. Then I'm going to take 405 divided by 405, which will be 1. And then finally, 810 divided by 405 will be 2. Okay, and once you complete that division, you now have reduced row echelon form of your matrix, otherwise known as Swiss cheese, right? So now we can celebrate, because once you have this matrix, we can convert it back into a system of equations and just kind of read what the solution should be. Okay, if we look at this first row, this is telling me 1x and 0 y's is equal to 1. The second row is telling me 0 x's and 1 y is equal to 2. So that means that if we were to graph these 2 lines, and I don't know exactly what they look like, maybe they look something like this. It doesn't matter. What this matrix is telling me is that the point where these 2 linear equations intersect each other is the ordered pair 1, 2. X is 1, y is 2. That's the point where they intersect. So we can say that the solution for this system of equation, the solution set rather, is simply the ordered pair 1, 2, and you have to put the ordered pair in parentheses. And that's exactly how you'll type it into Alex. Okay. So maybe press pause, take a moment to sort of gather yourself, because that's the process that we're going to have to go through to solve some of these problems. So I will do another example here with you guys, but I just want to sort of quickly recap what we just did, because I cover this in the PowerPoint. So the first thing that we did was we took our original matrix, okay? And then we asked ourselves, what number should I multiply by each of the rows so that 2 and negative 3 become the same value but with opposite sign? And so there, all we did was flip-flop the numbers. We didn't care about the signs right off the bat. We just said, okay, let's multiply the first row by a 3. Let's multiply the second row by a 2. Okay. So once we did that, we multiplied those numbers through the entire row. So 3 got distributed onto 2, 5, and 12. 2 got distributed onto negative 3, 6, and 9. What we ended up getting was this intermediate matrix that had 6, 15, and 36, negative 6, 12, and 18. Okay. Then we added those numbers together, and we got our first 0. We put those new numbers on the bottom row so that we had a 0 in that first position in the bottom row. Okay. Then we turned our sights on the second column where the 15 and the 27 are. We said we need to match those numbers somehow by multiplying, right? So we did this crisscross pattern where we took 27 and multiplied it on the top and 15 and multiplied it on the bottom. We also took care to say, well, those are the same sign right now. So we need to introduce a negative sign so that those coefficients would be opposite signs. So I said, let's go ahead and just do a negative 27, multiply that on top, multiply 15 through the bottom row. And then once we did that, we got this matrix over here with some really big numbers, okay? But the important thing is that we're focusing on that second column, and we got negative 405 and positive 405. Okay, now that those match, we can add the rows again and replace row 1, okay? Once we did that, we got this new matrix with 2 zeros exactly in the positions where we needed them, okay? It didn't matter that all the other numbers were changing. We don't care about that. We're really doing this very methodically, trying to get those zeros first, because once we have those zeros in place, then all we need to do was divide each of those rows by the first non-zero number in those rows. So we took row 1 and divided it by negative 162. We took row 2 and divided that by 405. And then that's how we got reduced row echelon form. Okay. So once you have reduced row echelon form, then we can say to ourselves, well, we have our solution. X is equal to 1, Y is equal to 2, and then we can move on with our lives, right? So remember, the process is, it might have a lot of little steps, like a lot of little multiplication and addition that you're going to be doing in the calculator, okay? You have to stay organized. But the big steps are that you need to get the zeros first, and you do that by doing that crisscross pattern, multiplying, and then you add the matrix numbers down the columns to get those zeros or to get an elimination. Okay, so if you don't get a 0 when you do that, you've made a mistake. Go back and look at the numbers that you multiplied because you're trying to get a 0. And if you don't, then you're not going in the right direction. Okay, once you have the zeros in the correct positions, then you can divide those rows by the first non-zero number that are in those rows, and it should be fairly easy to get the ones. The last step is just to interpret this matrix as a system of equations because that will tell you the ordered pair where the two linear equations intersect each other, okay? So, we'll look at another example shortly, but I do want to keep in mind that there are some different scenarios that you might run into, and there are some problems in ALEKS that ask you just to interpret what a matrix is telling you, right? So basically, to convert that matrix back into a set of equations. Okay. Okay. So there are 3 possible outcomes that are kind of represented by these example matrices. And these are each in reduced row echelon form. The way that you can interpret them, though, is just convert them back into a system of equations. So let's take a look at this first one, okay? So if we're looking at this first matrix, and remember that some of the matrices that you're going to see in ALEKS do have an X, Y, and a Z column, so just watch out for that. This first row is telling you X is equal to 1. The next row is telling you Y is equal to 2. And then the final row is telling you Z is equal to -1. Okay. So if you have a number for each of those variables, then we say that we have one solution. okay? We have one solution, and this is a three-dimensional matrix in that we have an x, y, and a z dimension. So we call this an ordered triplet. Our solution would be 1, comma, 2, comma, -1. We haven't talked about 3D space in this class, but it should be a fairly simple thing to sort of generalize from what we've been doing with the 2x3 matrices. Very same thing. If you have an ordered triplet or an ordered pair, then we call that one solution, okay? The second thing that you might run into is you may get a matrix that looks like the one on the right. And if we convert it back into a system of equations, then we should see that the first row tells us that 1x is equal to 1, so x is equal to 1, that 1y is equal to 2, and then finally we have this equation where we have no x's, no y's, and no z's. So that's really telling us 0 is equal to -1, okay? And that might make you scratch your head for a moment, but if this is correct, if we did the steps correctly and we got 0 equals -1 for one of our rows, then that implies a contradiction. What I mean by that is that 0 is not equal to -1. That's completely nonsense. So anytime you look at a matrix and you did everything correctly, you crossed your T's, you dotted your I's, and you get this nonsense statement, well, then we know that 0 is never going to be equal to -1. So we can just say that there is no solution for this system of equations, okay? So you don't want to make that more complicated than it is. If you look at that last row, usually, if you get nonsense, 0 is equal to something that's not 0, then that is a false statement. There is no solution here, okay? Next, then you may get a matrix where in the first row, you see x is equal to 1. In the second one, that second row tells you y is equal to 2. But then we get this last row where x, y, and z are all zeros. So we have 0 is equal to 0. Now, this is different from the previous example where we had 0 is equal to -1, because this is a true statement, right? But all of our variables disappeared in that last row. What do we do with this, okay? Well, if this is the situation that we're running into, where 0 is equal to 0, that's always going to be true. And that tells you that you have infinitely many solutions to this equation, okay? So there we can just say, oh, we have infinitely many solutions. Let's just move on with our lives. But what does this mean? Well, in the first video, I said that there are 3 scenarios for your linear equations. So let's back up a little bit. Okay, this is fine, right? If we have one solution, then that means our lines intersected each other, right? So that's okay. If we have a nonsense statement, like we did in the second possibility, that means that we have 2 linear equations that are parallel with each other, which means that these are never going to intersect, okay? Since these are parallel and they don't have an intersection, well, then that system can't possibly have a solution, okay? And it will show up in your matrix as a nonsense statement, like 0 is equal to -1. And then finally, we had this scenario where maybe we have a line, and when we graphed it, we graphed the other equation, and it fell right on top of the first line, okay? If that's the case, then those lines intersect each other at every location, and that's why we say that they have infinitely many solutions, okay? So even if we're talking about those line graphs, or if we're looking at matrices, we should be able to see through those 3 different scenarios, okay? So what I want to do is go ahead and go through one of these word problems that you're going to see towards the end of your homework in ALEX. Okay, so the way that you're going to approach these is first you need to read the scenario that they're giving you, and then you need to sort of write down a set of equations that describe the scenario. So let's jump right in. It says Jessica went to Quick Trip and bought 3 large Dr. Peppers and 5 regular-sized Snicker bars for $16.47. Okay, so whenever you read that sentence, you should be able to write this as an equation. We're going to let X represent Dr. Pepper's and let Y represent the Snickers bars. So we have 3X plus 5Y, 5 Snickers bars, equals 1647. Okay. Then we'll read the next sentence. That one says Brandon went to Quick Trip and bought 2 large Dr. Peppers. So that's going to be our X coefficient, and 7 regular sized Snickers bars. So we're going to write this as 2X plus 7Y equals, and that costs a total of 1824. Okay, we have those 2 equations, and all this problem is asking is if X represents the cost of a large drink, the Dr. Peppers, and Y represents the cost of a regular sized Snickers bar, determine the system of equations that represent this situation. Okay, well, we are able to just read off those numbers and write them as an equation. So this is the system that we're looking for. Okay, so this is just a match problem. So let's just be very careful here because there's a lot to look at. There's a lot of places where we can make little mistakes. So let's go through each selection individually. We have 3x plus 5y equals 1647. That looks good to me. We have 2x plus 7y equals 1824. This one looks like what we wrote down. So let's just make sure that the other ones are incorrect so that we haven't made a mistake. So we have 2x plus 5y equals 1647. Well, that's not what we have at all. So I'm going to X that one out. We have 3x plus 5y. That looked good up until they put 1824. We have 1647. So that can't be right. And then these have negative 3x plus 5y equals 1647. Well, not only is that the wrong number, it really wouldn't make any sense to go to the QT and buy -3 Dr. Peppers. So we're going to cross that one out just because those numbers don't match. So the only one that worked here was that first option. Okay, so take your time with that so that you can select the correct answer. All right. All right. Okay. Let's take a look. Now, there are going to be some problems at the end of the homework that say, read this scenario and then not only set it up as a system of equations, but go ahead and figure out how much does 1 Dr. Pepper and 1 regular sized Snickers bar cost. So if you're trying to figure that out, what we need to do is take that systems of equation that we made and convert it into a matrix. And with that matrix, we can begin using the Gauss-Jordan elimination process and figure out how much 1 Dr. Pepper and 1 Snickers bar cost. So let me write this down real quick. We have 3, 5, 16.47. We have 2, 7, 18.24. Okay. And you really don't want to be super committed to any of these numbers. They're going to be changing as we go through this process. So let's just see how this goes as we step through the Gauss-Jordan elimination process. Okay. So just keep in mind, X represents the price of a Dr. Pepper, and Y represents the price of 1 Snickers bar. Okay. And then we can start that elimination method process. So the first thing that we needed to do was focus on matching these first two numbers here. Okay, so we have a 3 and a 2, and all we're going to do is crisscross those numbers. I'm going to put 3 here and 2 here because we're focused on the X column. Okay, now I know that 2 times 3 is going to be 6, and 3 times 2 is going to be 6. So we're going to try to match the columns, but we want opposite signs for those X coefficients. Okay, but 2 times 3 and 3 times 2, those are both going to be positive 6. And so I get to add a negative sign to one of those. I always just add it to the top, just so I don't have to do any thinking about that. Just add it to the top so that now we'll get a negative 6 and a positive 6. So we can go ahead and do the multiplication now. So we have negative 2 times 3 gives us negative 6. Negative 2 times 5 equals negative 10. And negative 2 times 16.47 equals negative 32.94. Again, these numbers are going to change. They're going to be strange, but you have to trust the process and know that we're getting to the right place. Okay, at the end, everything will kind of reveal itself. Now we're going to take this 3 and multiply it by every number in the bottom row. So 3 times 2 is 6. Going to put a 6 here. 3 times 7 is 21. 3 times 18, 24. 3 times 18, 24 is 5472. Again, you don't have to be in love with these numbers, but we're going to trust the process. And the thing we wanted to see was that these numbers now match, right? We have a negative 6 and a positive 6. Okay, so don't worry about the other numbers. Those are going to change. But now the next step was simply to add down the columns and replace row 2. So we're going to add the numbers down the columns, and we'll use these new numbers to replace row 2. So negative 6 plus 6 give you a 0. Negative 10 plus 21 gives you an 11. Negative 32.94 plus 54.72 gives you 21.78. And these are going to be the new row 2. Okay. What that means is that I'm going to write a new matrix. And now I'm going to put 0, 11, and 21.78 in row 2. And then row 1 can stay the same. I'm going to leave it as negative 6, negative 10, negative 32.94. Okay. And then we can start that process over again, because now that we have a 0 here, we are now looking at the Y column to try to get a 0 here. So for step 3, we need to match the column Y coefficients by doing some multiplication and making sure we have opposite signs. So we might do a little check here and say, do we currently have opposite signs? Negative 10, positive 11. Those are opposite signs. Okay, so here, because they're already opposite signs, I don't need to introduce a negative sign. I already got a negative and a positive. All I'm going to do is crisscross the numbers. 10 goes down here, 11 goes up here. Again, I'm not concerned about the sign because I already have opposite signs. So now I can go ahead and multiply through the row, and we'll see what we get. Okay, so 11 times negative 6 is going to be a negative 66. 11 times negative 10 is negative 110. and then 11 times negative 3294. We're going to get negative 362.34. Okay. Again, we're not married to these numbers. I don't care that they're big. I don't care that they're decimals, but we're just doing the process. Okay. Now we're going to do 10 times 0, 10 times 0, which is 0, 10 times 11, which is 110, and then 10 times 2178. 10 times 2178, which is 217 and 80 cents. Okay. That's my new matrix. The thing that I was looking for was that the numbers in the y column match each other with opposite sign, and that's exactly what I got. So again, if they're not the same number and they don't have opposite sign, then you need to check something because you won't be able to proceed with the next step, which is just to add the columns again. But this time we're going to replace row 1. Okay, so when I add these up, I'm going to add down the columns. I'll see what I get, and those are going to replace row 1. So first, negative 66 plus 0. It's negative 66. Then I have negative 110 plus 110. Guess what? You got that elimination that we were looking for. Okay. Then finally we have negative 362.34 plus 217.80, and I got negative 144.54. Okay, and this is going to be our new row 1 because we have the 0 where we want it. And earlier in the PowerPoint I said, well, if we just took these two rows, row 1 and row 2 from here, we'll have our numbers where we want them. Okay, so what we can do is just take these rows that I boxed in and make a new matrix. So we have negative 66, 0, and negative 144.54. That's going to be row 1. And then I can take this row 2, which is 0, 11, and 2178, like so. Okay. These two guys that I boxed in, I put them together into a single matrix. And then the last step to get the ones is just to divide by the first non-zero number in each row. So we're going to take this row and divide that by negative 66. Then we're going to take this row and divide that by 11. And then we'll see what we get. Okay, so we took negative 66 divided by itself should be 1. So we have 1 here. 0 divided by, well, anything, but in this case, negative 66 should be 0. Finally, we have negative 144.54 divided by negative 66. That's going to be 219. Okay. And then last step, we're going to take 0 and divide that by 11. We get 0. 11 divided by itself is a 1. And then 2178 divided by 11 is a 198. And so if we trust the process and we do these steps correctly, we should end up with this Swiss cheese reduced row echelon form of our matrix, which tells us that the price of 1x, the Dr. Pepper, one large Dr. Pepper costs $2.19, and then one large or regular size Snickers bar Y is equal to 198. So there, we know how much the drink costs, and we know how much the Snickers cost for just one. Okay. So hopefully that gives you at least a couple of examples that you can look at and reference. You might have to watch these videos a couple of times, and you may have to practice here in Alex in the homework a couple of times before you really start to get this process. But I assure you that this is doable. It may be a lot of little steps, but it really is just plugging the things into the calculator that are the hardest part. Okay. So what I want to say to you guys is this is kind of the last piece of knowledge that we're going to cover this semester. And it's not the easiest thing, but definitely make sure you're watching these videos, going to Math World and asking for help, because the only way you're going to get this down is by practicing. If you continually are just feeling overwhelmed because it seems like this is too many steps, I don't know how I'm going to remember this all, you're wasting a lot of time and you're wasting a lot of emotional effort when you can just be putting your head down, going to Math World, and getting it done. So the best remedy for your anxiety is just to practice, practice, practice. And you know, they're looking forward to seeing you guys in Math World. So make sure you're going there and asking for help. Okay. If you have any questions, go to Math World. As always, you can shoot me a message. You can shoot me a message in Canvas, or you can shoot me a message in my Google Voice number. Okay. But I will see you guys next week when we'll begin reviewing for the final exam. Okay. So best of luck.